Welcome to the first video lecture on magnetism. In this one, we'll look at magnetic forces and fields, and we'll be really concerned with the magnetic forces on a charged particle. So this follows along into chapter 21, sections 1, 2, and 3. So please follow along in the textbook. This is a kind of a tricky topic, so please make sure you're doing the necessary work so that you fully understand it. Without further ado, magnetic forces and fields. A magnetic field is the area around a magnet in which another magnet would feel a force. Now, every magnet has two poles, a north and a south pole is how we define them, just two poles, and opposite poles attract and like poles repel each other. And magnetic field is the area around that magnet in which another magnet will feel a force. We talk about every magnet having two poles. That's no matter, and if we can get it down to the smallest particle of what it is, it's a spinning electron, and within a quantum physics, we don't think of it as actually like spinning like the Earth would, but it has a spin state where we quantize the energy. It's either an up or a down spin, and even that has a north and a south pole for that spin state. So we have yet to be able to produce a monopole and observe it. It may exist theoretically, but we have not been able to observe a magnetic monopole. So every magnet has two poles, and the area around it is where another magnet would feel force, is the magnetic field. Magnetic field lines, similar to electric field lines, show the strength. They're representative of the strength and direction of the magnetic field. The magnetic field, once again, points out of the North Pole and into the South Pole. And a magnetic field will always start at a magnet. It doesn't just kind of originate it would just pop in there, but it starts at one magnetic point and goes to the South Pole on another one. If the magnetic field lines are really tightly packed together, then it's a stronger magnetic field. If they're spread out, then it's a little bit weaker. So we have the magnetic field here, and there's also, you have the direction, so from north to south side of a magnet. If you take out a compass is really just a tiny little piece of metal that's been magnetized, and it will point in the direction of towards geographic north. The north side of the compass will point that way, and that actually is attracting towards the southern magnetic pole. So the southern magnetic pole is in the northern hemisphere. It's actually in probably northern Canada, just north of the Hudson Bay. And the northern magnetic pole is down in the southern hemisphere. It's out, I believe, over near somewhere else on Australia. I'm not quite sure where it is, because you know what? I've been pretty much living in the North Pole my whole life, so I don't really have much concern with that. But the bar magnet within the Earth is there, and it's kind of the idea that there's a bar magnet. It's due to the molten iron core that we have. So we have a solid iron core, and then we have a molten core that is moving. And as we'll see later, moving charges create magnetic fields. So there's this flow of molten lava, molten iron and nickel core that is moving around and creating this magnetic field. And there's actually a really terrible movie. I think it was called The Core. I'm trying to remember. But a couple of years ago, probably back when I don't know, a couple of years ago, 2 or 3, maybe a few more, where they had to go and restart the core and get it to move. And they had this thing that drilled into the center of the Earth, this big the ship, and it was made out of this material that they called unobtainium. And I just remember it. I'm pretty sure it was a core. Go watch a trailer for that. It's pretty ridiculous. So, yeah. Magnetic fields. Southern magnetic pole near the North Pole. All right, now for the actual real physics part of this. A moving charge within a magnetic field will experience a force. So, and I'll say that again. A magnetic field will exert a force on a moving charge. There are two things. One, the charge must be moving. Stationary thing doesn't happen. So the charge must be moving. Second, there must be some component of the velocity that is perpendicular to the magnetic field. If the charge is moving parallel to the magnetic field, it will experience no force whatsoever. So there must be some component of the velocity that is moving perpendicular to the magnetic field in order to experience a force. If it's moving completely perpendicular to the magnetic field, it experiences the maximum amount of force. So we have an equation here that will help us calculate this. And for those of you that know a little bit about calculus, this actually involves cross product. And we'll talk about that a little bit in a second here. But the magnetic force that a charge will feel depends on the magnitude of the charge, Q. V is the speed that it's moving, or we could say the velocity. Right now we've taken out all the direction from this part here. And B is the strength of the magnetic field. And sine is the angle it is with respect to being perpendicular. So if it's 90 degrees to the magnetic field, sine of 90 degrees is 1, so it'll be the maximum amount of force. So if we were to include direction and use notation for calculus, we'd have the cross product here, and there would be the velocity vector crossed with the magnetic field vector. This is just something in case you see it later on in a different situation. Now, magnetic field is measured in Tesla, and to give you kind of an example of like what a Tesla is, the Earth's magnetic field is about half of 10 to the fourth, or well, I guess it would be like 0.05 micro Tesla, whereas about like the magnetic field within an MRI machine is 3 or 7, somewhere in that range, 3 to 7 Tesla. So the force on a charge, on a moving charge, depends on the speed, the amount of charge, and the magnetic field, and the angle it is due to in relation to the direction of the magnetic field. All right, so how do we figure out the direction of that force? Because if you notice in that equation, there's no actual direction that we have. Within this, if we have the velocity, we're going to use what's called the right-hand rule. We know the velocity, we know the magnetic field, we can figure out the direction of the force. So the right-hand rule involves, get ready for this, your right hand. Yep, that's right. Right-hand rule involves the right hand. Now your thumb is a line goes along in the direction of the velocity of the charge, and you can take out your hand, like watch the video, move your hand around right now. So your thumb is moving in the direction of the velocity. Let's say if a charge is moving to the right, and the magnetic field is coming out of your chest and going away. So the charge is moving to the right, and the magnetic field is straight ahead out in front of you. You then now want to curl your fingers. You curl your fingers up to like a 90-degree thing, and that's going to be the direction of the force. It's coming like straight out of your palm. So the idea is you kind of curl it like that. You can kind of even do it if you want to have like your pointer finger going in the direction of the magnetic field, and then your middle finger kind of makes it like you're flicking somebody off a little bit. But either way, the thumb goes in the direction of the charge, fingers move in the direction of the magnetic field, and then you curl them up to the direction of the force felt by that charge. So here are a couple of different little examples of what would happen. So we have a magnetic field here. I'm going to start from left to right in situation A. We have a positive charge and a negative charge moving along here. They're moving parallel to the magnetic field, so they will experience no force whatsoever. And now we have the middle one. We have a charge that's moving perpendicular straight across at a 90-degree angle to the magnetic field. It's moving kind of towards us, almost out of the screen, and that is the force would be directed upward. And if we could easily summarize that if it was the same charge moving in the opposite direction, the force would be directed downward. Now we have to our right, we have the charge moving here at let's say some angle. There's a component in the perpendicular direction, and that's all that we're concerned about. We're not only concerned with the perpendicular component of the velocity, and once again the force is upward, but since it's not moving completely perpendicular to the middle situation, as in the middle situation, the force is going to be a little bit smaller that it would experience. In a magnetic field, the force applied on a moving charge is always perpendicular to the velocity. And because of this, there's no work done by the force, by the magnetic force. In this situation, by the force due to the magnetic field. Now, in drawing a magnetic field, you need to have the arrows go into the page. So this is, we have arrows that represent the magnetic field and field lines, and we draw them as arrows. And so the end of an arrow, in this case, it's going into the paper. So we draw that the arrow, the end of it, it looks like an X because it's kind of like the feathers on the back of an arrow. Whereas if it's coming out of the page, it looks like the point of an arrow, so it's just a circle with a dot. So when you're going into the page, it's an X. When you're coming out of the page, it's a circle with a dot. Now, in this case, we have a charged particle. It's moving in a magnetic field. The magnetic field exerts a force. This causes the charge to move in a circular manner, and it goes around in a circular path. So here we have a little bit of a comparison between an electric field and a magnetic field. Now what we're really concerned with is positive charges, because we generally are worried about those, and with negative charges, it just is the force is applied in the opposite direction. Now, within a electric field, a positive charge or a negative charge, but any charge will follow a parabolic path or a parabolic motion as it moves into the field. Whereas within a magnetic field, the charge will follow a circular path. So we'll have this circular path due to the charge. All right, three questions here just to finish up the lecture. First, what happens when you cut a magnet in half? Let's say you have a bar magnet and you cut it in half. What now do you have? So what happens to the magnetic properties? Second, where is the Earth's magnetic south pole? So where is the magnetic south pole of the Earth located? Third, the sun emits a stream of charged particles. This is called the solar wind that move towards the Earth at very high speeds. And most of these particles here are they're called alpha particles. They're just positively charged particles, basically protons. And a proton is moving towards the Earth at 500 kilometers per second. So kilometers per second, important to notice that. At this point we're looking at, the Earth's magnetic field is 5.0 times 10 to the negative 5th Tesla, and it's directed parallel along the Earth's surface. What is the direction and the magnitude of the force on the proton? So you need to think about using the right-hand rule and that equation. Thank you very much. Make sure to put your answers in online. Follow along in the textbooks, and I'll see you tomorrow in class. You guys are great little scientists. Keep it up.